Good afternoon, everyone. Our speaker this afternoon for the first half of this track is going to be Daniel Lindsley. He's going to be speaking on building a Python-based search engine.
How are you all? Did you have a good lunch? Yes. All right, good. So, my name is Daniel Lindsley. I am from Lawrence, Kansas. Not this Kansas, but this Kansas. But really, I'm from the internets. So I run a little web shop called Toast Driven. Might you see this? And I do consulting in open source. And I'm the primary author of a package called Haystack, which is a Django app for pluggable search. But we're not here to talk about Haystack today. So the goal of what we're going to talk about today is to give you a broad overview of how search technologies work. Because if you're familiar with other technologies like RDBMSs, they're not the same beast. They work very differently, and understanding how a search engine works can give you insights as to how to work with other engines. What we're going to try not to do is have all of you write yet another search library, because we really probably don't need that. So there'll be code and a link to the slides at the end of the talk, so bear with me. So why should you care about search? Doesn't the Googles handle that? Well, turns out there's a lot of good reasons to have in-house search. One of those is that things like Google or Ask or Microsoft's and Yahoo's technologies, they have to scrape web content, which means they get HTML soup and they have to parse through it and try and pull out any kind of meaning. Getting reasonable, proper content out of that can be a big nightmare. Another good reason is you know your data model better than any scraper does. They just have HTML. They might have ad content in there, they might have RSS feeds, all kinds of things that aren't pertinent to the content that's really being displayed. Or maybe you're weird and you don't do web apps like I do. So, good reasons to have, let's talk about some core concepts. Search engines are all document-based. These are not row DBs in your average RDBMS. You're never, ever just grepping through a string. That is like the worst thing you can possibly be doing. We don't want to be looking at big text blobs every time we go to run a query. You'll hear me talk a lot about inverted indexes. We're going to get into this in a few minutes, as well as stemming, n-grams, and relevance. So, as with all fields, there's a ton of terminology, so we're going to go through some stuff really quick so that what I say throughout the rest of the talk has some meaning. So we're going to talk about these terms, and we'll start with engine. The engine is the black box you hand a query to and you get the results from. The good examples of open source engines are things like Solr, Elasticsearch, Zapier, Whoosh, and many others. Sphinx is an example. Documents. Documents are the text blob. The text that you send to a search engine is one of the most important things that you can pay attention to. And additionally, you probably want some additional metadata to describe what that text blob consists of, where it came from, titles, other attributes and stuff. Corpus. A corpus is just the collection of all the documents in the index. Stop words. Stop words are words that are basically filler. These are things like and, the, but, and whatnot. Words that don't contribute a lot of meaning, but appear very frequently in documents. Stemming. Stemming is finding root words. And we're going to look at this a little bit later. Segments. Segments are the data that make up the overall index. Because you may be dealing with gigabytes or terabytes of data, shoving everything in one big file really doesn't scale well. So a common technique is to shard things down into what are called segment files, which as a whole make up the index. Relevance. Relevance are the algorithm or algorithms you may apply to the results you get back out of the search engine to determine how well a certain document or result may fit an individual query. Faceting. Faceting is drill down. If you've ever been on Amazon.com, that left-hand bar that lets you say, hey, I want a camera that's a Canon in $200 to $400 range, and lets you drill down, that's faceting. Boost. Boost is a way to push up certain kinds of results in the result set so that they bubble up to the top. So let's start at the beginning. Let's talk about indexing. Indexing is taking a document, the blob that we were talking about with metadata, and pulling it into the engine and performing transformations and storage so that we can query on it later on. There's 4 major breakdowns: receiving and storing documents, tokenization, generating terms, and indexing those terms. So let's start with documents. Documents are the simplest thing we will talk about all day. They are not, ever, not. They're not a row in the DB. Really, no, really. You really want to be thinking, like I've said, a blob of text and some metadata that goes with it. Like I've said, quality is the most important thing. What your users search on is what you index is what your users will be able to search on. If you put a bunch of junk in, they're going to get garbage results out. Documents are a very flat concept. A lot of people try to work relations into search engines, and it never ends well. You want to be thinking things like, I like to think of search engines as kind of the original NoSQLs after Berkeley DB. So don't try and put relations in. It doesn't really work well. And the one thing I really want you to take away from any of this, because it applies everywhere, is you want to denormalize the living crap out of anything you're indexing. Because the more you can shove on that has meaning, again, text quality is important, the more you can shove on that has meaning onto the individual documents, the better they will bubble up in results, and the better results your users will get when they search. So a document looks really familiar. If we represent it as, say, JSON or Python, it's just a dict. There's really not a whole lot to it. It's a text blob with optional metadata. From there, and you can imagine all kinds of ways to store that data. Tokenization is the process of taking that big text blob and breaking it down into little individual word-sized chunks. Typically, what you'll find most engines doing is splitting on things like whitespace. They'll lowercase every single token that they get out of that, filter out all those meaningless words like and the and but and which you're going to hear a lot of, and stripping punctuation, et cetera, et cetera. Many times this is configurable so that you can tweak it to match your document set. The point of that is to get some nice, neat, normalized little tokens out that you can work with when querying. So we mentioned stemming, and so that's where we'll go to next, because now we've got documents, we've got a list of tokens in those documents. The next thing we want to do is be able to take those mostly normalized tokens and get something even better out of it. So by doing stemming, so if you do something like grep, you're processing through a file stream, and it's literally just checking, hey, is it here, is it here, is it here, is it here? That's horrible when you've got gigabytes and gigabytes and gigabytes of stored document content. So when we do this tokenization and the post-processing, we're really close to what we want, but not quite. So stemming is the process of finding the root word. Examples of this would be like test becoming testing, because the ing ending is not particularly meaningful, or searchers becoming searcher, becoming search, because we want to find root words so that if someone misspells something or if there's a pluralized form, we can get back down to that root word and store one variant rather than 20. These then become the terms in the inverted index that we'll be querying on. And if you apply the same tokenization and stemming to the query, what you get out of a user's query is the exact same thing as the terms you're shoving in the index. The downsides of stemming are that it really only works for the language it was built for. Most stemmers that are out there are pretty much English only. There are other languages, but they don't work particularly well, and they're poorly supported. It's really, really painful, even in high-quality search engines. And they're really hard to make work cross-language because the structure of German or French is not the same as English. So this is a really bad shortcoming. So there are many ways to solve this. The approach we're going to look at today is n-grams. As I said, it takes care of some of the shortcomings of stemming. We're going to introduce some new problems, but overall it's typically worth it. What n-grams consist of is taking a window and passing it over your tokens. And that these new little terms that come out of this moving window are what become your terms in the index as opposed to a stemmed version of the word. And we'll see an example of this in a few moments. So for instance, if we do a typical n-gram and we assume a gram size of 3, we've got 3 characters, HEL, ELL, LLO, and then we jump to the next term, or the next token, and generate a complete list of terms based on the tokens that we have. Now, that's great, except that typically you're probably not typing in LLO as a query. So what we want to do is find another way to approach this shortcoming. Edge n-grams typically solve this. So what an edge n-gram will do is it will pin to a side of a token. In this case, with a gram size of 3, we still have that HEL, but instead of moving the window along, we're going to generate different gram lengths so that we have a gradually more and more complete word that becomes our terms. And then again, once we switch to the next token, we start with this gram size of 3 again, move to 4 and 5. And as you can see, these terms are much more likely to be in a user's query than LLO. So this is great because it gives us a, first of all, it works great for autocomplete because the user can start typing something very short and you can start immediately feeding results back to them. It's also good because it works across other languages because it no longer relies on the grammatical structure. You're just simply looking at tokens. And if the word starts the same way in a different language, it'll match well to whatever terms you generated. Cons are that when you use n-grams or edge n-grams, you generate a lot more terms. And as a result, storing all those terms can be kind of a problem. Or at least it bloats up on space. And initial quality of search can suffer a little bit because now you're dealing with fragments and something that you may not have meant to have matched now matches. So an example in Python might look something like this. We set a minimum and max gram size like we did on the previous slide, 3 to 6. We have a dictionary of terms that we're going to be storing out of this. We pass in a list of tokens, run through it, make sure we grab position information, as well as the individual token, and then we just, for the range of our gram size, pass a window over it and shove the newly generated term into our terms. So now we've got documents and we've got n-gram terms. The next step is storing this in a way that we can actually query on. That comes in the inverted index. The inverted index is the heart and soul of the search engine. It is how things work. You can think of it exactly like a Python dictionary because it's largely key value. Those keys are the terms that we just got finished generating with n-grams. And it's all the terms from all the documents. So you can imagine taking a large body of text, generating tons and tons and tons of edge n-grams. Each one of those that you generated becomes a new key in that big inverted index. And of course, this is across all documents, not just one document at a time. The position information that we were grabbing out of the previous example of edge n-grams is important because we can say, how far into the document did this word appear? We can also say, hey, how many times in this document did this word appear? And of course, we want to store document IDs so that when we search, we can map things back to the data that we've stored. So an index, as I said, might just look just like a plain old Python dictionary, and you'll be storing the individual terms like blob and text, if you had an n-gram size of 4, for instance, and document IDs such as document 1524, and blob appeared at position 3 of that example we saw on a previous slide. Once you have this index generated, the problem then becomes querying over it efficiently. Like I said, if you have this huge, massive data structure hanging out, you can't put it all in one file and search over it effectively. So there's lots and lots of ways to do segments to break that index down for efficient querying. Many projects follow, there's this famous Java project called Lucene, which is really, really good at search. But we're going to cheat because it's easier. So in the example code that I've got, we're going to just use flat files. We're going to take those n-gram terms that we generated when we ripped through the big blob of data, and we're going to hash them. And we're going to take part of that hash, the leading part, and use it to map it onto a file in the file system. This limits the number of files that we've got down to something that like a Unix-like system can handle, as well as ensures that if you've got a given n-gram, you can easily map right down into the proper segment file that it's associated with. We're going to keep terms in always sorted order, and we're going to use JSON to store the document and position information, not because it's particularly performant, but because it'll work well across other languages or other tools. So an example implementation might look something like this. I mentioned we're going to hash, so we just take the term, pass it in. We're going to take a length of 6 on the hash just so that it's short and keeps a reasonable number of files in the file system. And we just simply do a simple MD5 on it, get a hex digest, and return the first 6. As far as saving a segment, this isn't in always sorted order. The code I'm going to present to you at the end is always in sorted order, but it's simply just appending onto the file the information. And we're going to tab delimit because all of our tokens have already been white space separated, so there's no chance of tabs showing up. So by getting to this point, we've already covered creating the terms, storing them, storing the documents. We've got enough information that now we can start query on them. Querying breaks down into a query parser, index reader, and scoring at a high level. So let's dive into the query parser. Typically, the purpose of a query parser is taking a user's handwritten query, maybe they have advanced knowledge of it, maybe not. You can think of this as analogous to SQL, and parsing it out into something that the engine can start tackling. You're going to process all the elements of that user's query the same way you did when preparing the document for indexing. So an example, trivial Python implementation might look like something like this. We've got a list of common English stop words, and we're gonna really, really cheat in this case, and we're just gonna split it up, check that the token's not in stop words. If it's not there, we're gonna toss in our list of tokens, and then we're gonna make n-grams. It's the same kind of stuff we just did when we were preparing the index. Index reading becomes easy now because we have this list of edge n-gram terms. We can simply go through, hash them, and we can find whatever file we just stowed them in a very quick, efficient lookup. And we just rip through all the tokens that all the terms that we generate from a user's query, grab all the hashes, go into the files, pull out the results, and collect the position and document information. This is a little big. I apologize if it's small. But it's basically the same kind of stuff. We make a segment name so that we know what the file name of the term is. Check if it's there. If it's not, we just return nothing. If it's there, we go through and we start ripping through the file. And there are more efficient ways to do this, but we're splitting on the tab for now so that we've got the term and the info. If we found that term, say we entered hello as our user query, and we found HEL in the segment, we're going to pull out those results because we found a match. And collecting the results is simply a matter of just going through all the terms that were generated from the user query and applying that load segment to those terms. Finally, so where we're at now is we've got a user's query, we've tokenized it, we've made terms, we've gotten all the results together, but they're out of order. They have no meaningful order for the query that we generated. So what we're going to do with scoring is reorder that collection so that it means something based on the user's query. There are tons and tons of choices of scoring algorithms. We're not going to go through all of them. A major one is BM25. It's very famous. You can look it up on Wikipedia, and it's pretty interesting. There's also what's called the phased scoring query, and Google's PageRank is a great example of this. This can be anything. You may decide that words that include Bob are really, really important, and you're just like, Bob, you're always up at the top, buddy. So, an implementation of BM25 looks something like this. I can't explain it, I'm sorry. So, as a quick demo of this, I have indexed the first 1,500 documents of the Enron email data set. So, if anyone has any correct for polite company terms they'd like to search on, fraud? Okay, let's do fraud. Oh. Demo fail. I'm mad. Okay. I'm sad because this literally just worked before I came down. Why you don't do demos and talks. Thank you. So let's talk about some advanced topics, shall we? I'm not going to cover any code on this, but diving into this would be probably a great exercise for you. God, I sound like a college professor. Horrible. So faceting is made out to be a lot of things, but what drill down really consists of is for all the terms that are provided, giving accurate counts on the number of documents that contain those things. So when you're on Amazon and you're digging through digital cameras and you say Canon, and they give you a count, that's really all faceting is. It's just that count. But that count is important because it lets the user know both what things are matching within the document set as well as how many are there. Say there's only 2 Canon cameras on Amazon, which will never ever happen. You might be like, well, wow, they don't really have a really great selection. Maybe I need to go elsewhere. So an implementation would probably look like collecting all the terms, counting the length of the unique document IDs for each of them, and then just order by descending. Because once you have those terms and you know how many things matched and how many documents were there, you just order by the count and you can provide back something that's useful to the people who are using your software. Boost happens during the scoring process. Literally, it's just saying, hey, we've got a score that we generated, but we want to artificially bump things up, so Bob gets a bump up. If it's matched, you just tweak the score. It'd be literally nothing more than modifying the BM25 relevance score. Another common one is something like more like this. What more like this provides is basically contextually similar documents. So you've got this huge list of terms that you generated when you indexed. You know all the terms that were in that document, and you can also find other documents that have a very similar set of terms. And an implementation would look like collecting all the terms based on documents. So you probably need an alternative data structure to store a document to term mapping. And then just sorting simply based on how many times a given document was seen in the set. This is really, really simplistic, as is most of this presentation, just because it's to get a high level. Engines like Solr and whatnot use much more complex solutions like natural language processing, as well as other types of contextual analysis to get a much better quality result. So I told you not to go invent a search engine, and I went and invented a search engine. Code is up on GitHub, BSD licensed. Feel free to poke through. I've annotated the whole source, so it should be easy to dive through. Here's a list of some additional resources. Lots of good stuff here. The IR book is fantastic and largely free on the internet. It's worth it for any kind of textual processing and just learning about how information retrieval kinds of topics work, as well as a bunch of other things. And thank you very much. As I mentioned, the slides are up on SpeakerDeck at this URL once I make it public. They'll be up just after this talk. There.
We have about 6 minutes for questions. If anyone would like to ask a question, please line up behind that microphone. Quick note on process, ask your question, I will repeat your question, and then he will answer it.
So just to kind of review, where do you think the cutoff is between rolling your own search engine and just basically trying to figure out how Solr works and implementing it yourself in your
To me, the code I put up, I would say no one should ever deploy in production. It is horrific on I/O because you're literally writing with every single term. You probably want something that does something more like indexes a bunch of documents in memory and then does a commit and flushes them out to disk. So to me, it's a learning exercise. It was great to go through and like solidify things for myself at a high level. I'd encourage you to go ahead and do that if it's of interest to you. but it rapidly becomes one of those things where you'll probably start hating life if you have to support it.
Hey, can you speak to the relative importance of things like stop words when you're using something like BM25 or TF-IDF that takes into account the frequency of words? Or better, refer to any resources that show those kinds of differences?
Sure. So when I showed this, I kind of glossed over some things. So what like he mentioned, BM25 does a great job of filtering out words that are extremely frequent. I can't explain the math on this, but essentially, if something has, I believe it's like a 75% chance of appearing or something, or a certain, it's like 75% repeats, it'll just be ignored. So the way the relevance score is calculated is, it's kind of weird. It's a trip to read on Wikipedia.
You can tune it 75%.
Yeah, right. That the B0 that's up there, that's passed in as a quark, that actually is document length. If you set that, it'll adjust score slightly, as well as the K modifier is just used to like kind of normalize the range. So like when you do scoring, you don't get a 0 to 100% match like you might have seen in older search engines. You get a weird floating point number. And it doesn't really mean a whole lot because it's just based on the document set as well as the query. But like the moment someone changes the query even slightly, you can get very different scores. So that's why you rarely see people exposing scores on the front end of things because they don't mean a lot. Now, BM25 and I believe, I think the phased approach also handles this. They kind of already deal with excluding things like stop words and really frequently repeated words. The problem is that if you lean on just that, you don't get in my opinion, you don't get as good of quality results because other things might be repeated very frequently. Say you're in the Python documentation, the word Python is everywhere. And it can be ranked lower by a score out of BM25 just because of how frequently it appears, even though it's not really a stop word. Also, if you filter out stop words ahead of time, you save on lots and lots and lots and lots and lots of disk space. It's really more of like an I/O saving crutch.
How are you doing? What are some techniques and algorithms for doing a full phrase matching?
So the question was, what are some techniques for doing full phrase matching? It really depends on it depends on how the query is parsed and how the index is read. What'll typically happen is you'll find that a query gets broken down into something that's more like a tree with operators in between them. And so like if you double quote something in a query, chances are that'll get pulled out into like, if you imagine a query tree, it'll get pulled out into an exact match node. And so it'll generate terms. So like in the case of n-grams, not everything uses n-grams. In fact, most things default to stemming, but n-grams work better in a lot of circumstances. So in that exact match node of this query tree, it will still generate those edge n-gram terms and look them up, but probably generate them for the max length of the word. So like in the case of hello world, both terms are 5. So generate an edge n-gram of 5 for both of them, look them up, find documents where it has both of those words, and then look at the position information. And if the positions aren't right next to each other, you discard the result.
So you're just manually filtering the result set then to find the documents that actually have that phrase.
Essentially, yes. Now, some engines take a different approach, and they will store full matches. You have to realize most search engines are like nearly infinitely configurable. So you can make it do whatever you want, and this is a really, really simple view of things. But some engines will store, full exact matches. The thing you don't want to do is, try and go through an entire blob, because as soon as you do that, performance just drops.
Thanks a lot.
Mm-hmm. Any other questions?
I actually have one.
Yep.
How does n-gram searching work with languages that make heavy use of prefixes, like Greek, for instance?
So I can't speak to Greek, but if you have, it depends how it's prefixed. If it's prefixed with punctuation, like you say, like it's hyphenated or something, typically you'll be splitting on punctuation anyway. If you're talking about, I'm trying to think of examples like in English of common prefixes.
Epicenter.
Pre-post.
Epicenter.
Epicenter. So another thing that I've kind of hidden away in this talk is that, say for instance, Solar or Lucens, their default implementation generates edge n-gram sizes from 2 to 15. So even though it doesn't help in the case of prefixing, it does in postfixing. And the way you get around it for prefix things is typically generate n-grams instead of edge n-grams.
Got it. Ladies and gentlemen, Daniel Lindsley.
Thank you very much.